Scale factor is just a comparison of two different shapes that are similar, how much bigger or smaller they are in relation to each other. So a dilation in geometry is a reduction or an enlargement of your original figure. And k is the variable that we use to describe this, and it is the scale factor. Now when k is bigger than 1, you have an enlargement. Something is twice as big, or it's 3 times as big. Now, if k is smaller than 1, if it's half as big, it's 2/3 as big, it's a reduction. If you ask yourself, is it an enlargement or a reduction before starting, this next part will not even matter. To find the scale factor, you should put your new length or distance, whatever it is we're doing, over your original length or distance. Now don't panic. If you don't remember which one goes on top, it doesn't actually matter. There's a way that you can safeguard yourself. But the way that I like to think about it is N comes before O in the alphabet. So new is on top, original is on the bottom. Now in this picture here with the rectangles, we're going to give them some dimensions. This is going to be a 3 by 2 rectangle, and the other one is going to be a 6 by X. In these figures, it says the shaded figure is the new figure. That's how we're going to work these 4 little problems. But if it doesn't tell you, we're always going to assume that the figure on the left is the original and the new one is on the right because we read from left to right. But here, the dark one is the new one. So we can see that it's an enlargement. How much bigger is it? Well, this one is nice and easy to tell. This one we can just say if the original was 3 and the new one is 6, it's twice as big. But to try that out, we're going to put the new one on top. We're going to put our original one on the bottom. And we do indeed get that k is equal to 2. So that means that all of the new dimensions on the darker rectangle are twice as big. So it means that this x is twice as big as its corresponding 2. And so it's 4. If there were other dimensions, like the diagonal, you could just also assume that whatever the length of this diagonal is, the one on this figure will be twice as big. So let's try these, because these are sneaky. These ones deal with distances, not lengths. This little point over here is called a vanishing point. If you go from one figure and you perfectly pick up the exact same spot on the new figure, they will converge into something called a vanishing point. These are the distances we want. So let's put down a 4 here. So 4 goes from here to here. 12 will be this entire length from the big moon to the small moon. Now it looks like this little teeny moon is 1/3 the size. This 4 is 1/3 of 12. Well, yes, 4 is 1/3 of 12, but that is absolutely the wrong answer for the scale factor, and it's because this one deals with distances. We have a reduction on our hands, and we know that we need to get a small number. So let's get our original, let's get our new distance. Our new distance is just 4. So k, it's got the new guy on top, 4. Now, the original distance is not 12. That's where a lot of people fall apart. The original distance goes from here through the 4 and through the 12. So that distance is actually 16. It's 12 plus 4. So now you can see that this is only 1/4, not 1/3. And I promised you I would show you what happens if you do it backwards. It's fine. If you start off the whole thing saying, hey, this is a reduction, great, and you put the 16 on top, the whole distance, over this little one on 4, you have 4. Is this little tiny moon 4 times as big as the original? No. So all you do means you've done it backwards. We are just going to flip this over to get k equals 1/4. You just turn it over. So it's an easy fix. Now we're going to get rid of all this mess. Let's go down here and try these two. Let's assign some values to these suns. We want this length to be 12. So that's going from the tip of the sun to the vanishing point. And this little piece here is going to be 6. Again, it looks like it's this little part here is half as big, but you have to take the whole distance into account. First of all, enlargement or reduction? Enlargement. Second step, let's get our k. K is going to equal the new, which is the whole entire big gigantic distance, 12 plus 6, which is 18, over the original distance, which is just 12. So, and no, you cannot cancel these 12s out. Addition ruins your life. You have to complete it first. That's 18 over 12. When we reduce that down, taken out a 6, we get 3 over 2, or 1.5. And it's believable that that could be 1.5 times as big. Now, sometimes I'm going to give you a problem that will look like this. This distance is 8, and this distance is 2x, so we can't compare those. This distance here is 6, and this is going to be x plus 1. In order to find out if this is an enlargement or a reduction, we need to follow one line of sight. We can't compare the 8 and the 6. That's not going to help us. So we need to find x first. But these things lie in perfect proportion. This little segment here is proportional to this segment. And then, let's get a new color. This segment here is proportional to the 6. So we can set up a proportion that actually kind of looks like what it's supposed to be. The 2x over the x plus 1. And that's going to equal the 8 over the 6. All we have to do, now you could reduce that 8 and 6, and it probably would make your life a little bit easier, but let's go with what we've got. 2 times 6x is 12x, equals 8 times x plus 1. We're going to clean up this whole mess. 12x equals 8x plus 8. Let's bring this 8x over there. So we get 4x equals 8, and hooray, x equals 2, something very usable. I'm going to plug that 2 in, and I'm going to say that this is now equal to 4. I'm going to plug it in here, and this is equal to 3. It's very much the same kind of numbers that we saw in the other one, except this guy is a reduction. It's a reduction. So we have to remember, let's put our new distance, it's this guy, 8, over our old distance, which would be 8 and 4, which is 12. If you reduce that, you get 4 goes into that twice, 4 goes into that 3 times. It's 2/3 the size. Now, if you use the bottom line, you should get the same thing because it's the same exact set of lightning bolts. So that should not change things. So if we put 6, it's our new distance. Our original distance is the 6 and the 3. Do not forget to add them. When we reduce that by dividing out a 3, we're still going to get 2/3. So it doesn't matter which line of sight you use. So try them out on the next page. Remember to answer the question, is it a reduction or an enlargement? And then you won't mess up the way the fraction goes. And the other thing to remember is this 16 is only going from this little vanishing point to this first heart right here. The whole entire distance, this 8, is only going from this heart to the big red heart. You need to remember that. All the figures here are similar. You can pretend they're the exact same shape. They have just been enlarged or reduced. You may need to solve for x in the last one. I'll see you in class.